thrust is a propulsive force which moves rockets through the air. So as you can see in this little demonstration, or this diagram here, that the rocket is doing work on the system, pushing out exhaust. Since Newton's third law is every action has an equal and opposite reaction, that opposite reaction is this thrust here, pushing the rocket up into space. So it is generated by the rocket engine itself. And one of our equations we learned in Physics 151 was this conservation of energy equation, which is the K initial stands for kinetic initial plus potential initial, which is that U, plus work external. In the case of a liftoff of a rocket, both kinetic initial and potential initial will be 0. So the only work exerted onto the system would be the thruster itself. And then it's a pretty easy equation. It's going to equal kinetic final plus potential final plus delta E thermal, which is the thermal dissipative, any dissipative force. So heat, friction, the friction force of drag, and things like that. They're dissipative forces. So we can use, so there are many types of rocket engines out there. For the sake of time, I am only going to be talking about two: the chemical and ion thrusters. But there's also nuclear thermal and the reaction control system thrusters, which are thrusters attached to rockets to kind of position them, make sure they're in the same or an exact location where they need to be. When SpaceX had one of their rockets land on their platform, that was highly reaction control thruster systems. So they're cool, but I can't talk about them. I spend hours, legitimately hours. So liquid chemical rockets. Liquid chemical rockets use two propellants. They use an oxidizer. It's usually liquid hydrogen, but it could be any other sort of thing that would create that would continue that explosion. So it uses a fuel and an oxidizer. Fuel would be kerosene. Oxidizer is that liquid hydrogen. They are pumped into a combustion chamber. When added with a spark, explodes. That explosion travels through the throat and out the exhaust, or out the nozzle as exhaust. And the thrust equation for it would be the mass of the flow rate times the velocity, the exit velocity, plus the change in pressure multiplied by the area of the nozzle itself would give you that thrust. Now, these liquid chemical rockets produce an immense amount of thrust. They produce anywhere from 845 to 914 kilonewtons, which is 190 to 205,500 pounds of thrust. It's quite amazing, the amount of thrust achieved by these rockets themselves. So, and we'll talk about them just a little bit more. So because it uses two propellants, a oxidizer and a fuel, you can't use them in space. There's no air in space. So their main use is escaping Earth's atmosphere, right? It's, again, because you have no air in space. But another great tool for using liquid chemical rockets opposed to solid or other types is they can be throttled, which helps which helps with kind of anything. So say if something would go potentially wrong, you could cut the rocket off at practically instantly. So during liftoff, or at the time of liftoff, they full throttle, and because you only have two propellants and you don't want to run out right away, during the end of its transition, they throttle back and use as much as they can, right? So the mass of one of the rockets is about 474,600 it's about 570,000 kilograms. Now the total fuel mass is 474,646. So it's practically just made up of fuel, right? You want to maximize how much you're actually getting into space, right? So you want to be efficient. You want to use as much space as you have for fuel. The total burn time on this rocket here, which is the SpaceX's Merlin rocket, is about 2,016 seconds. So it burns at roughly 235.4 kilograms per second. But that's not exactly right. We're going to come back to that. Okay. So another rocket another thruster is the ion thruster, and these are really cool, extremely futuristic, and hopefully we get better research within the next 5-10 years. So ion thrusters use a single propellant, so you don't need a fuel and an oxidizer. You need xenon in this case, and they use xenon gas because it is a heavy non-radioactive gas, non-radioactive gas. Now, what happens is the propellant is pushed through this magnetic field, right? You have an electromagnet here, and it creates a magnetic field. The cathode strips an electron from the xenon, making it positively charged. Turning that into a plasma, which that's plasma. It's a positively charged gas. So then that plasma gets ejected out the back at 40 kilometers per second, which is an insanely fast speed. But it doesn't produce a very high thrust force, only for the fact that not a lot of the ionizing are molecules. They're not big masses. So they're not a large amount of mass. So it's kind of stripping it, creating that plasma. It looks cool, and it does produce a thrust force, but it's very small, and we'll talk about that as well just pretty soon. So ion thrusters, their main uses are to keep geosynchronous satellites to maintain their orbits, and for communication satellites to stay in their desired location. So they produce a low thrust force, about only 5.3 newtons, but they have the ability to run for years. So I made some calculations here. So the single SpaceX Merlin rocket burns at, once again, 235.4 kilograms per second, but the Falcon 9 rocket itself has 9 of them. So the amount of mass that burns, just 235.4 times 9, is 2,118.6 kilograms per second. My car weighs, granted, I drive a Prius, I'm sorry. It's 1,379.8 kilograms. So it's just under two Priuses a second. If you could think about that. So a single rocket burns through that much propellant that much mass in 2,000 seconds. When you attach 9 of them, max burn is 224 seconds. So it goes from 33 minutes to roughly about 4. Is that right? Yeah. So the total amount of time of thrust achieved from these is actually 7,607 kilonewtons. But in a vacuum, there's less drag force. So you're actually achieving 8,227 once you actually hit space, which is, I wrote it down here, 1,710,000 to 1,849,500 pounds per foot of thrust. It's an immense amount. So, lastly, the Hall thruster, the one they're researching, back how it says it could burn for years, only 30 kilograms, so 66 pounds of xenon gas could burn for 6,630 hours of thrust, which is approximately 726 days. So, what's more efficient in a way? And how can we take the Hall thruster and produce a higher amount of thrust to say leave Earth's atmosphere or things like that? All right, and that's everything. Thank you very much.